today we have Dr. Ahmad Abdulkader, who is a well-known industry expert with over 50 publications and patents in the area of machine learning and artificial intelligence. He's currently a distinguished scientist at Facebook AI Applied Research. He invented Deep Text, which is a deep learning text understanding platform that is widely used throughout Facebook and open source community. Prior to Facebook, Dr. Abdulkader was the co-founder and CTO of Voice AI. Am I pronouncing it correctly, or Voice?
It's a Voice, yeah, but your pronunciation is valid, definitely. Yeah.
It's Voice AI, which was acquired by Cisco in 2019, and Voice built a widely used meeting platform that became part of Cisco's WebEx. He also worked for Google, where he built the optical character recognition and verification of Google's BookSearch. Ahmad is one of the main contributors to Tesseract, the most widely used open source OCR engine. In addition, he was one of the pioneers of StreetView at Google. Ahmad was one of the main creators of StreetSmart, a computer vision platform for privacy protection and scene understanding in StreetView. At Microsoft Corporation, he was one of the pioneers of the Handwriting Recognition Technology that powers the Microsoft Surface devices. He's also one of the earliest contributors to the Arabic OCR and Handwriting Recognition. He's the co-inventor of the first Arabic OCR Engine. He studied at Cairo University, where he got his bachelor's and master's degree in electrical engineering. At McMaster, he received his second master, I believe, and at the University of Washington, he got his PhD in computer science. Pretty impressive achievements. They're very happy to have you with us, and thank you for agreeing to give a talk. Floor is yours. Thanks.
Thank you. Thanks for the introduction. That's really appreciated, and thanks actually for the audience for attending. It's my pleasure and honor to be with you guys. So today I want to talk about technology and automation of labor. We hear a lot about how AI is actually eating jobs and how automation is influencing the labor market in a certain way. And these are my reflections on it. You know, I really want to, you know, it's an attempt to get to the bottom of it. How did this happen? And I'm not going to talk about the solutions. Maybe I'll allude to them towards the end. But really, I feel that actually understanding the roots of the problem, why is this happening? Is this part of something that has been happening all the time? Is important. And this will help us a lot in understanding and maybe figuring out what to do about it. I have to say, so since last year, in the next few years, I'll be involved more with the social work community, where harnessing technology is actually one of its grand challenges. And I'm looking at AI actually not just as a problem for our societies, but it could also be an opportunity actually. And I will also allude to that. So this is a topic that is of really great importance, at least to me, and I feel it's a very important. It's a topic of the hour, and it's a great pleasure for me to talk to folks in the computer science community, in the AI community. I think we as a community have to really seriously think about that. As contributors to this field, we also need to think of the impacts, the adversarial impact of it, and think about ways to to not just add value, but mitigate the cons as well. All right, let's see. So, needless to say, I think the pandemic experience speaks to this very well. Although I prepared the slides before that, but I think the changes in the workplace that has been happening over the years, especially the last couple of years, have been really very profound. The workplaces that we are engaged with these days are very different from what they were 30, 40, even 10 years ago. So, virtual, here we are, attending a talk over Microsoft Teams or over Zoom. Zoom is a household name. It's even a verb in certain circles. We can, expect it to reach each other using messaging or even email. Even email is outdated. A big part, especially in the technology community, is looking at telecommuting and not having to be physically present, at least some of the time. At Facebook, or I should say at Meta, we are seriously considering, and significant percentage of our new hiring will be remote. The idea that you have to own and spend a lot of money on real estate it's not clear whether this is justifiable anymore. We're also seeing, significant improvement in productivity. However, and not just in the technology communities, but in other communities as well. And I will share some data towards the end. All right, so what's happening? So this gentleman, Mark Andreessen, I think I'm betting that most of you guys are young enough to not know him. He was the inventor, one of the authors of Netscape, which was one of the very, very early browsers. This was my first browser, and it was afterwards completely, Internet Explorer, overtook its market share. But he is a very influential venture capitalist in Silicon Valley. His opinions and his views are very, very important. People pay attention to what they say. So he said that in 2011. He said software is eating the world. Yeah. So what exactly did he mean, and was he right? So let's see. So you guys, not sure. Some of you have been around during the dot-com bubble. Things have changed quite a bit. So there are a dozen or so companies, Facebook, and Uber, and Google, and others. They're sparking a lot of controversy. I think Facebook named the news the past month or so is a testament to that. The way Uber has changed, commutes all over the world, not just in California or in the US, is well known. So taking a look at the sort of a financial facet of this, you see something kind of awkward. Technology companies are not really known to have a high PE or ratio. That's the ratio between their earnings and price, which is the total of the number of shares times the share price compared to the earnings. Typically, that reflects how the sort of the prospect of the company. If this P ratio is high, this means the prospect of the company is very high, and people expect it to be worth way more than the earnings that it's coming. So stock markets really does not look favorably on these companies. Even a company as big as Apple. Tesla is an exception, and I have to say this chart is a little outdated, but still this fact holds. This is a very funny example, and I bet most of you actually are not aware of this. There was this company, huge bookseller called Borders. They were the bookseller. They had lots of really physical location. Barnes & Noble was another one, and digital books was a very uninteresting area for them, that they decided nah, we're not going to be making big investments in this. Let's ask Amazon to help us with that, and the rest is history. Borders doesn't exist today, and we know where Amazon is. So, and that's not very far in time. So we're essentially living a revolution of sorts, and we'll talk more about this in details. Why is that the case? So software companies are really poised to take large swaths of the economy. If we were to monitor it, the share of software companies of the economy, it's definitely on the rise. And as a result, some businesses will just cease to exist in their traditional form. So why is that happening? So let's start from the beginning. It used to be that software is offered as floppy disks and CDs. People buy their software and they receive it, physically. They install it on their desktops or laptops and start using it. That's hardly the case anymore. There are probably a few exceptions here and there, but nobody does that anymore. Software as a service is the thing. So essentially, the software is in the cloud. Your data is most probably in the cloud. Maybe some of it will be local. Maybe this cloud is actually internally. So, if the data is really confidential and people don't feel good about having it in the cloud, they have on-prem clouds, and software gets updated over time. There's no software cycle. When I used to work in Microsoft, the Windows shipping cycle was a year and a half. That's not the case anymore. People make daily updates, if not hourly updates, and users do not even notice that there are changes. Some of them do. There's a lot of A/B testing also going on. Different people may be using different versions of the software as it happens. And SaaS is a key element in that. Without SaaS, this revolution would not have happened. It's an ingredient, but this was really the initial step in this revolution. So just to look, 7 decades into the computer revolution, so to speak, and 5 decades since the invention of the CPU, microprocessor, and 3 decades after the rise of the modern internet. All the technology is starting to disrupt many industries. Using SaaS, it's very easy to launch software that billions of people can use. Billions of people are speaking hundreds of languages, different cultures, different values, different standards. This was unheard of, believe it or not, like 20 years ago. So how did this happen? Cost is a big component of that. It used to be that, to have an internet application in, around the year 2000, it would cost you around $150,000 a month. These days, it would cost you on Amazon, less than $1,000 a month. And if you're a startup, you can even get that for free by the value of the credits that you can have, if you're an accelerator or something like that. So cost has declined dramatically, and building an app that people can use worldwide, have access to it, is almost near zero cost. The problem right now is the proliferation of these apps. Is how do you distinguish yourself as an app for people to find you useful and to use it? Of course, that happened because of the sort of super linear growth in storage, CPU, memory, all of the components, and the cost, of course, of these components going down. Something like AWS, Amazon Web Services, and similar things in the cloud and Azure, Google Cloud, and Azure, like that, made it almost trivial for anyone to host an app in the cloud. So today, the largest video service, known in the world is Netflix. It's a software company. Dominant, music companies like Pandora, Spotify, Apple Music. These are the dominant music companies. Who would have thought? And their revenues really do reflect that. And they are growing. There's no sign of even asymptoting or saturating at this point in time. Entertainment, the video game industry is rising exponentially. Pixar is one of the best movie production companies. Disney had to buy it and make it. Could not afford to just compete with it. People are as old as as myself can remember a company called Kodak in photography. I mean, people hardly talk about it anymore. People talk about Shutterfly, Snapfish, Flickr, and other companies. These are all companies that were displaced by software companies. You look at business services. Google is the largest direct marketing company in the world. It's a software company. Skype and Zoom. We're talking about Zoom. They are really the biggest telecommunication companies. LinkedIn is the biggest these revenue numbers are outdated. They are the largest recruiting company in the world. All are software companies. Car industry, needless to say, we're all hearing about the shortage of supply in cars, even used cars, largely because there's been the chip production has been stalled due to the pandemic. So the cars are essentially software industry has a big say in the car industry, and we haven't even started talking seriously about autonomous vehicles yet. Companies like Tesla and Cruise and Google and Apple will be the new car manufacturers in the near future, or will be a big part of car manufacturing in the near future. Hiring software engineers, machine learning engineers, AI engineers is a top priority for the big car manufacturers. If you would have said that even 5-6 years ago, this would have been a joke. Other industries that are waiting to be disrupted are retail industries. So the Walmarts of the world. Walmart survived and was able to overtake like Kmart and other, because they had great logistics, great data analysis and analytics to tell them exactly about how to handle the logistics of the distribution, storage, what's available in their physical stores, brick and mortar stores, and who would have believed that Walmart would have a major industrial research department called Walmart Research? It exists today. It has actually some of the really set of bright scientists. It has been really crucial in keeping Walmart alive and competitive against a company like Amazon. Examples in delivery like FedEx, pricing airlines is a very competitive and very hard problem. Without software, I think many airline companies will and are going out of business. Other services like agriculture, oil and gas, financial industry, PayPal generated more than I would say, I think it's closer to 2 billion in one quarter these days, and they are a software company again. So going over this and looking at it in a sort of a macro level, getting a historical perspective, it's really astonishing. What's next? Expect healthcare, expect real estate. Education is being disrupted as we're speaking, literally. So software, is really an opportunity for new Silicon Valley style startups to invade existing industries. Concepts like shared economy that Uber pioneered is being, extended to, you may have heard, to restaurants, to the food industry, to even like a company like Instacart. It's really, we're not seeing, even as I mentioned, any form of saturation yet. So it's fair to say over the next 10 years or more, there will be battles between incumbents in certain areas and new insurgents, really driven by software. This is really fits the the term coined by famous economist Joseph Schumpeter, when he said this is really creative destruction. You're destroying a whole set of industries, and you're constructing new ones. We're going through fundamental changes. All right, so that's one basic element. That's sort of the sort of background or infrastructure, if you will. Next comes machine learning. I belong to sort of the early generation of machine learning. We didn't use the word AI because it was a bad thing to say. It was a very it seemed like sci-fi back then, and it had a bad name because of the hype that was associated with it in the 80s, especially in countries like Japan and stuff like that. The machine learning and AI mean different things, but they are used interchangeably. So what is machine learning? Let's take a little bit to describe it, look at it sort of in a maybe formal way. So machine learning algorithms can automatically learn programs from data. They essentially learn programs. Instead of writing them from scratch, or instead of these programs being written by human, we actually learn them from data. More data means more ambitious tests. So these days, web search has a big AI component. That was not the case, by the way, all the time. Until I left Google in 2009, there was almost no machine learning in web search. It is actually very interesting to see Google embrace AI this much. One of the reasons I left Google was that there was not enough AI. And neural nets, we published a paper about convolutional nets in 2008 or something like that. And it was a struggle because people thought I should have been using graphical models instead. So it's very interesting to see the transformation that happened and how a company like Google embraced machine learning. Spam detection, folks may remember how prevalent spam was. Today, it's largely not a big problem. You can argue it has been largely solved. Recommendation systems are very common to see on Amazon and other e-commerce sites. Ads that we all mostly feel that they are annoying, but to be fair, they've been getting better and better and being more relevant over time. At least some of us see them like that. And there are many other tests. I'm not going to go through them. Some of them are very well known. Some are very, very specific and apply to certain industries. For example, drug design. So how do we learn as humans? There are various ways and various forms and various types of learning that exists. The simplest of which is depicted in this figure. It's called reinforcement learning, which I think many of you are aware of. That we essentially, nobody sits us down and explains to us that a chair has 4 legs, has a seat, and it's really different than a bed because the bed also has four legs. And what exactly is the difference between a chair and no, we learn by example. Our parents show us chairs and show us what the non-chair is, and we build our own concept of chairs without actually having to know exactly. Like, it's very hard for any one of us to articulate what is chairness exactly. Why did I didn't see all the dogs in the world, but I can identify a dog even for a breed that I did not see. I cannot sit down and say what exactly would make this animal a dog and not a cat. So we learn by example, and this learning is stored and expressed and articulated in a certain way in our brain, not in a way that we can articulate in a good way. There are various ways of doing that. This is one form that we'll get back to. It's called reinforcement learning. Essentially, there is a critic who is watching the learner and gives positive or negative feedback about how a learner responds to a new input, and either reaffirms what the learner does or corrects and critiques it. There are many types of learning: classification, regression, ranking, recommendation. There are many others. The most important, the most prevalent that's being used in industry is classification. Essentially, you get an input expressed as a vector. It could be fixed length, it could be variable length, and these set of inputs could be discrete or continuous. And discrete, they could be ordinal, they could be categorical, and you're supposed to classify it to one of the possible, at least one of the possible outputs. Some problems you actually you can actually classify it as more than one class, and there are so many variants of that, as you probably know. Classical example is spam detector. Here's one way to represent the input is a Boolean vector. Each bit represents which words were present in the email, and you're supposed to. This is a binary classifier. You're supposed to say, well, this email is a spam or not. There are the 3 major types of learning, but there are many, as I said, are supervised learning, unsupervised learning, and reinforcement learning. I would say the vast majority of the systems in place in production is supervised learning, where we actually learn from data that has been annotated by a human, directly or indirectly, and we use that to build a set of machine learning components, typically, classifier. As there, the demand for annotated data, and I will actually, allude to annotated data as an opportunity towards the end. The demand is so high that we cannot keep up with it as a community. People have been looking into unsupervised learning as a good alternative. We do not need, as humans, millions of examples to learn. There's strong evidence that we use unsupervised learning because data is not random. There's structure to data that we can figure out as we see examples of it. We need a little bit of supervised data, of annotated data, but we need a lot of unsupervised data, and that's how we form our learning concepts. We will see, in the next few years, significant improvements and milestones achieved in unsupervised learning. There's strong evidence, though, that the kind of gains we get from unsupervised learning is orthogonal to the supervised learning, in the sense that unsupervised learning is probably not going to replace supervised learning. Instead, it's going to augment it. And we're trying to figure out exactly what, how. Reinforcement learning is gaining a lot of ground. There's a certain example that I will refer to that will show how is this happening. The basic elements of a machine learning solution to a problem are really mainly three. It goes on three. Form of a representation of the input, the way to evaluate a possible candidate solution, and an optimization technique that shows us how do we search for solutions. Representation really defines the hypothesis space of the learner. What does the solution? What form the solutions come? Are they hyperplanes and multidimensional space? Are they a set of heuristics that we search in the space thereof, or what exactly? And hypothesis space actually determines to a great extent many factors or many aspects of the learning system. There's a great deal of feature engineering that goes on. A domain expert would typically spend a lot of time coming up with inputs that go into a machine learning system. This is the traditional way of doing things. Recently, with deep learning, there has been more reliance on sensory signals, meaning that these are raw signals like images or audio or just plain text, without any further processing or cooking, so to speak, of features. It's not for every problem, but this has been gaining ground to the extent that feature engineering became learned as well. Machine learning is starting to replace even the traditional parts that humans used to do. As I mentioned, evaluation is a way of saying, well, is this a bad classifier or a good classifier? How do I test that I succeed or not? Optimization is how do I actually search in the hypothesis space, and it really determines to what extent I'm successful in learning and how fast can I actually search for solutions. It's very important to know that really the goal of machine learning is to generalize, not to memorize. There's no real world problem that is real and practical beyond toy problems that carries any value where you can find a training set that is adequate, that if you memorize, you're good. Any practical problem is just, there's no way you can find a training set which is big enough. And people talk about the curse of dimensionality. meaning that the more dimensions, the more inputs that you have, the more huge and big the space is, that becomes really impossible practically. It's fair to say not possible to find a training set that covers all of this huge, sparse, multidimensional space. So unless you generalize, there's no way you can learn. Whatever you're going to memorize, is totally useless if you're going to be evaluated or tested or applied on parts of the feature space that you have not seen before. Spam filter as an example. If we have a 100K vocabulary, and that's really a small vocabulary. So even if we have 100 billion examples, in the training set to memorize, that's a tiny space of all the possible combinations of 100K vocabulary email that has even 100 words, right? So it's not even like, we don't even need to do the math. So memorization is not the way to go. It's about generalization. The question is how to achieve that. So rule of thumb, there's no amount of data that is enough to learn. And the more data you get, the better you're going to learn if you can utilize this data, of course, in a good way. And that happens through the optimization algorithms and picking a hypothesis space that is valid or amenable to the problem that you actually are using. There's a very important theory. I mean, many people, many machine learning outsiders do not know this sort of dirty little secret. It's a sad reality, David Hume figured this like 200 years ago, is that no learner can beat random guessing over all possible functions to be learned, which is really depressing. So how come we learn then? Turns out this is a totally twist of fate. We didn't play any role in this. We're just lucky that this is the case, that the functions that we need to learn have certain characteristics. They are smooth, actually. So it's very hard to find a real world machine learning problem where the separation layer between classes, for example, is not smooth. You don't see abrupt changes in these. Machine learning algorithms apply this constraint in their search in the hypothesis space. Without that, it would have been really, really hard. They have to be limited complexity. If you're familiar with Occam's razor, in the absence of any evidence, the simplest explanations are the ones that are correct most of the time. So without these principles, we really cannot learn. And we're really lucky that, in the real world, these things exist. And machine learning essentially capitalizes on that. Compared to traditional programming, you can look at learning as, in contrast of philosophy, where that applies deduction. You start with certain axioms and you build on them using logic to prove certain theorems. That's really traditional logic. That use deduction. Machine learning is not that. It uses induction. So it can infer so many facts, so many conclusions, but it's not 100% certain about most of them. So you sort of trade off certainty and confidence and proof with significant growth in the set of premises and conclusions that you can actually reach, and that is really essentially induction. But you're not 100% certain about most of them, which is okay most of the time. So you can look at it as machine learning. I mean, it's not magic. You don't get something out of nothing. All it does is you get way more from much less. There's so few things in the world that we're 100% certain about. So we're okay. We're accustomed to actually dealing with things which are not 100%. We're not 100% confident that they are correct, but we think they're correct to a great degree of confidence. And of course, data is what we need. And guess what? We've been accumulating tons and tons of data. It is said that 90% of all the information in the world has been created in the prior 2 years. So, if you remember, the advance in the power of in the CPU and storage and memory. Add to that the significant growth in data, and you get the revolution that we're living today. Believe it or not, much of the concepts of deep learning and these fancy AI that advanced that we hear today, actually most of this stuff has been around in the 80s and 90s. I used to work on handwriting recognition, and we were using neural nets. We were begging speech people to use neural nets. Back then, they just didn't have enough data, and they didn't have powerful enough CPUs to do the training. Nothing changed, and suddenly, voila, there's a revolution in speech recognition, and it's essentially solved to a great extent. And there are really no new concepts. It's just the advancements of CPU and the availability of data, and of course the cost going down. Okay, now remember that day, 2016. Not sure whether you guys sort of know what I'm alluding to. Something very important happened on that day, and I'm going to talk about it in the next few slides. This incident has huge ramifications. It made us wake up to something really very interesting. So what happened? Let's talk a little bit about deep learning, and I mentioned it before. Deep learning is a way to actually a different way of learning from data. It kind of eliminates the feature engineering part. It deals with sensory data. Also, it's associated with models that are inspired by, we think, how the brain works. The brain, of course, is the least understood organ in the human body, but we have some hypotheses and evidence about how it works. And that inspired us to create machine learning models and technologies that kind of imitate that in a very, very naive way. And these are the so-called neurons. They have their history in the even early 50s, but they advanced quite a bit. They had a peak in the early 2000s, and then there was a decline in them for very silly reasons. And then there was a renaissance again 10 years ago, and we're living in the new second coming of neural nets these days. And the kind of results that we're seeing from them is really amazing. So what happened? There's this game called Go, which is actually harder than chess. I didn't know anything about it before, but I learned a lot since then. And it's actually much harder than chess, and doesn't lend itself to the techniques used by in solving chess, like essentially the search and bound type of an A-star kind of algorithms. And what happened is that a model built by folks in DeepMind using deep learning, it defeated 3-time European Go champion 5 times in a row without defeats. It's like, wait a minute, how did this happen? So okay, it decided to take on the world's best, the world's champion, Korean fellow, and China's top Go player predicted that Lee would not lose a single game. Lee himself is kind of a modest guy, and he said, well, I may lose a game or two. And guess what? He lost profoundly. Okay, and this was really a big deal. No one expected, even the authors of these models expected this to happen. It was using reinforcement learning. To be fair, it actually started or initialized the solution using non-reinforcement learning techniques, but essentially used reinforcement learning. And it was built by Google-owned DeepMind, which is a London-based company. There were similar, in related problems, similar results shown. So what happened? This graph depicts in a very rough way the growth in time in human performance and computer performance in learning. And we didn't notice this, but we've been seeing the hockey stick change in the graph. Some people were aware of it, of course, but nobody really predicted this growth. And it looks like we reached a point where in many problems, we are exceeding overperforming humans. How and when did this happen? it's actually interesting to see and know. So this poses a big problem, which is our topic of our talk today, is are we prepared as a community, as a society, to address this? If AI, if machine learning technology is going to replace jobs because we can do them better than humans, what do we do? How do people make income? How should we handle the society? And let's try to understand a little bit how is this happening, what it means. So there are really four types of jobs along two lines, whether it's routine or non-routine, repetitive, whether it's cognitive, intellectual, or manual. And if you look at these trends over time, historically, the routine cognitive and routine manual, routine jobs have been stagnating. They have been kind of automated for a while, but there has been growth in non-routine cognitive and non-routine manual over time. AI is changing that. It's replacing both of these jobs, and we're seeing stagnation in both of them because AI advances threaten these, and we're effectively replacing humans in these two types of jobs. So it's a game changer, and we're not talking about something happening in the future. This is happening as we speak, and it has been happening since the 90s, but it really accelerated, and we're going to see why. So in essence, and I think it's very accurate, we're living another industrial revolution, and many of the societal impacts that we're seeing happened before, and there's a lot to learn from the past experiences. Doesn't quite give us the full solutions, but it's very interesting to study what happened historically before. Not sure whether you know or not, but machines in factories in the 16th century, 17th century were sabotaged by workers because they saw that they were replacing them, and they were a threat to also employment at that time, and people did see the threat. So it's not the first time that we see that, and would be interesting. It's beyond the scope of this, but really interesting reading and to learn about how this was handled before. I'm not going to play this video just for the sake of time. It's a very interesting video, which I'm sure many of you have seen before. It's really for folks who haven't seen how much robotics have advanced. We really can build. We solved many of the really hard and core problems in robotics and navigation, and navigation has been great strides happening. We're still working on handling. We're still working on learning how to learning new problems that you haven't seen before. But we've seen lots of advances in robotics in the past few years. In medicine, for example, I think radiology is one of the professions that probably going to go away. And radiologists sitting and looking at your X-ray and diagnosing, that's going to rarely happen. You're going to have a role, but maybe in a very different way. In image recognition, it's like something like ImageNet. It's a data set that drove great advancements in computer vision. These days there are many, I can tell you, tens of startups in Silicon Valley that are basically trying to solve industrial problem, very specific in the domain specific problems using computer vision, anomaly detection, quality control, you name it. So like in computer vision, we have superseded many of the human capabilities like a few years back. This is a very interesting actually graph that shows this metric that economists like called labor productivity growth, LPG. And worldwide, in emerging markets, in the US. And you can see in the US it's kind of trending down, right? It's a fairly mature economy. So for less than half, the last decade, it's 2.8% from 1995 to 2004. So it's very hard. It's a metric that is very hard to actually improve. we are seeing significant improvement in LPG thanks to AI. And people have been expecting this for some time, and it looks like its time has come. Here are some examples that we're just, how much you saw how much has been growing. Let me give you some examples of how automation can actually improve, LPG. So as it stands today, there are 3.5 million, working in the motor vehicle industry. AVs can reduce this to 1.5 million. This is a boost of 0.17% to LPG. This is really significant, something that we haven't achieved in quite a bit. Something like call centers, just improving speech recognition and speech analytics can actually increase productivity growth by more than 1%. And we're just talking about two industries, random in many ways. Imagine, if we talked about more prevalent and important industries in our economy. So we're talking about serious productivity growth, something that cannot honestly be ignored. So it's another example of experiments that Google did in their data centers and how much actually they were able to, cut costs and improve energy consumption, knowing when to cool down and when to not do cooling in their data centers. Economists like to talk about GPTs, which are general purpose technologies like electricity is one of them, steam engines one of them. AI qualifies as a GPT. They are suited for augmenting or automating many tasks, and the core capabilities, of cognition and perception, they are so pervasive. They are, indispensable for many of the tasks that humans actually do today. So it's really well suited, to make an economic, profound impact. So yes, we are having, a disruption in the labor market thanks to automation. And you guys are aware, many politicians unfortunately use that to their advantage. Many of the populist politicians, and try to attribute this sort of disruption to immigration, many other sort of cultural war type of issues. But automation is really at the core of it. There's ample empirical evidence to that. So there's a set of really hard questions that we're essentially trying to answer. I'm putting them in the slide. So if a machine can do a job instead of a human, should a human be forced at the threat of destitution to perform that job? Should income itself remain coupled to employment? Like, we evolved a lot as a human society. There's freedom of religion. There are many things that we take now as rights, enshrined in constitutions. People talk about healthcare as a right and such. Would earning a minimal decent income should it be a right as well? Should you need to work to lead, a minimal decent sort of life? Is actually having a job the only way to obtain income? If machines are performing an increasing percentage of our jobs and not getting paid to do them, where does this money go? What do we do with this money? If it's possible that many of the jobs we're creating don't need to exist at all, and only do so because of the incomes that they provide, should we still keep them? These are very important policy and legislation that need a lot of discussion and need urgent solutions, some of which we don't have answers for, but at least we need to experiment with the solutions, start answering. Otherwise, we'll see the societal impact of that in the near future. And it's not as far as we think. UBI, which is I'm a fan of, I'm not going to hide my biases, is one solution. Basic guaranteeing universal basic income for an individual, and of course doesn't prohibit people from working, but it sort of guarantees a minimal living standard. You don't really need to work to get basic food and shelter, and we can decide exactly what are these basic services that we need. And there are many experiments with UBI. It's beyond the scope of this, but there's actually great results from them, and some of the myths associated with them turn out not to be true. That's somehow going to discourage people from work and stuff like that. It's not clear whether it's a 100% winner, and there are certain tweaks and parameters that we need to figure out. Recently, also, I was reading that Chicago is experimenting with some form of UBI, and I think you'll start seeing this happening at many localities. And I think it's a start of a solution. I don't think it's a silver bullet, but the answer is probably going to be along these lines. And finally, it's a big challenge, but within every challenge that we faced as a human race and society, there are opportunities. The way AI is deployed these days, it has lots of pros and lots of cons too, and it doesn't really have to be this way. The problem is not in AI, it's not in machine learning, it's in the way it has been deployed in our societies and how capitalism shaped it. And it really doesn't have to be this way. There are actually, in fact, opportunities, for example, to lower the cost of basic services like healthcare and education, and make them accessible to many vulnerable populations that cannot access them. There are ways also for AI to provide well-paying, dignified jobs, digital jobs. For example, I talked about the high demand for annotated data. This can be a very, of course, presented right. This can be a very good venue for many to provide digital jobs for them, and good chunk of that doesn't require really very high levels of education. There's a company that experimented with that called Sama Source. If you just go to sama.com, it was founded by her late founder is Layla Janah. She died very young of cancer, but the company still exists. They managed to lift around 50,000 people out of poverty in different parts of the world, Africa, South Asia, and at the same time, it's a $2 billion company that provides tons of data in the computer vision space for many of the big corporations that use AI. So these are examples of opportunities in AI that can actually we can definitely reverse the trend. As a computer science community and machine learning community, I think it's very important for us to be aware of that and be cognizant of the impacts of AI, and having that as one of our design principles, if you will, when we think of new ideas and new concepts. That's what I have. Thank you guys very much.
Thank you so much.
Thank you. I think I went over time, so.
Yeah, just a little bit, but
okay.
It was a very interesting talk. We touched on very important issues. So first in the audience, do you guys have any questions? Go, Angelica.
I have a question. There is an era where the performance of deep learning and all of artificial intelligence is quite limited. For example, some maybe medical systems, and if you don't know for sure how artificial intelligence works and what are hiding rules beneath its decision, how we can rely on the system to work in areas where the cost of an error can literally cost human life?
Yeah, so I honestly didn't hear very well, but let me reword the question and see if that's exactly what you're talking about. So you're saying that many of the machine learning models or AI models right now are not very interpretable, and we usually don't understand how things happen. Yes. How can we rely on them if we don't know how they work?
Yes.
Right. It's actually a very good point. Funny enough, so interpretability or explicability has been largely ignored by the machine learning community. It used to be like when I used to work in Bing, for example, when I used to give them rankers and say, hey, this ranker works well, it's like, can you tell me why this result is better than that result for this query. And it's like, what do you mean? I can't tell you. I can give you a very good classifier, but I can't tell you how it works. And we're only now starting to pay attention to this, and we're starting. There are very, good starts for making arguments about explainability for certain classifiers. I like to say, myself and another gentleman in MSR, we try to coin this term. It's called, the sort of the uncertainty principle of machine learning. You either get a really complex but really accurate machine learning model, or if you insist on explicability, you'll get something that doesn't work. So there's a Heisenberg principle of machine learning, so to speak. Now this is changing, right? And we're trying to change that. But let me be a little bit of a devil's advocate here, and there's something to think about. Do we really understand as humans why we make decisions? Or do we actually rationalize our actions? So explainability may be a bit overrated, a little bit. That is not to say that we shouldn't be working on it, but we like to believe that we are rational beings and we make decisions, that are founded and we can explain. But most of the time, and there's ample evidence that it's rather rationalization. So I think we need to frame explainability in a better way. Also, if I were to tell you that, fine, we will build explainable models, but this would mean that we're limiting machine learning to the concepts that we can comprehend as humans. We're not super beings. We have limitations, and we cannot really comprehend everything. But so if we were to do that, then we're limiting ourselves too. So yeah.
Yeah, so there's one online question I'm going to ask, and and that's about, we actually have more than one, but I'm just picking one of them for the sake of time. It's actually coming from Muhammad Isa, and he is asking that, considering the growth and the, I'm paraphrasing, of course, the growth in the technology, even at the high level education, not the low, like elementary school, even at the high level education, the things that we're learning in school might not be very beneficial in a few years. So what is your take on that?
Yeah, of course. People talk about, well, in general, not just machine learning, sort of a data literacy, that whatever you study, whatever you're going to specialize in, no matter what the discipline is, even if you're even humanities, there is a minimum level of data literacy that you have to attain. So significant changes in our education systems we have to go through over time. I think programming, for example, and some minimum level of understanding of data, very simple concepts like difference between correlation and causality, they have to be part of our education system somehow. Regardless of what you specialize in. As I said, I'm very much involved these days in social work. The discipline itself, and trying to understand more. They do lots of these randomized studies, and many of them are quantitative. And how do you talk about causality versus correlation, and statistical significance and the like? So, and this is a totally 100% humanities discipline. So, data and some minimum level, level of knowledge of and literacy in data is a must now. It's not an option anymore. And we have in the next few years to make profound, and they are underway, but they are not. It's not fast enough, unfortunately. Yeah.
Thank you very much once again, Dr. Abdulkader. Thank you for agreeing to give a talk, very interesting talk, and potentially.
My pleasure.
Thank you. If audiences have any other questions, I would be happy to somehow send the questions to you, or maybe directly connect them with you. Thank you again, and yeah, I think we're gonna end it at this point. Thanks.
Thank you. Thanks very much.